Hey guys, this is JBMon from Planting Seeds Tutoring. In this video, we will be talking about electron configurations. So have a periodic table handy. Don't forget to use my referral code JBMon20 to receive 10% off on your next tutoring package. So electron configurations give you a summary of where you can find electrons around a nucleus. You can't just find, see electrons just because there's a lot smaller than the wavelength of visible light, which is what we need to reflect off certain objects so that we can see objects. The number of electrons in the neutral atoms, as you already know, is going to be the same as the number of protons, and these electrons are going to be found in orbitals, which are found within subshells, and those subshells are found within shells. A shell is the energy level, or kind of like a ring inside of this Bohr model right here. So it's also the period number, the number of shell, or it's going to be the period number that you have, and that an element is found in. So within each of the shells, we can find specific subshells, and specifically, we can find the S, P, D, and F subshells as of now. And within each of these subshells, we can find a certain amount of orbitals which carry exactly 2 electrons. So right here, we have a subshell right here with an orbital inside of it with 2 electrons. And this subshell is carried by this shell right here, the magenta pink. So the S subshell can carry exactly 1 orbital. The P subshell can carry exactly 3 orbitals. The D subshell can carry 5 orbitals. The F subshell can carry 7 orbitals, which means that they can carry in total 2, 6, 10, and 14 electrons respectively. Each shell can carry one more subshell than the predecessing one. So the first subshell can only carry this one right here, the closest one to the nucleus, can only carry the 1s subshell. It can only carry one subshell, and that's going to be the S subshell. The second subshell, which is going to be the ring afterwards, it can carry 2 subshells. It can carry a 2s subshell, it's just one S subshell, which is on the second shell, and it can carry a P subshell. It's the 2p subshell right here. The third can carry an S, a P, and a D, and so on. So these shells, remember, are going to be the rings that we can draw out on a Bohr diagram. Right. So far, we know how many electrons can be found within a shell, subshell, and orbital, but we haven't discussed how these orbitals get filled. So there are 3 major rules which determine this. The order by which orbitals get filled with electrons follows a rule called the alpha principle, and according to the principle, the lowest energy levels, which are the shells, tend to get filled before the others. So here's how they would get filled in right here. We would have the 1s subshell get filled in first, then we would have the 2s subshell get filled in, then we would have the 2p and then the 3s subshell, then we would have the 3p and the 4s subshells filled in, then we would have 3d, 4p, 5s, etc. So all the way up to 7p. We haven't found any electrons or any elements with electrons post after the 7p subshells, so we haven't had a need for it yet. However, as you probably noticed, the 3D subshell actually got filled in after the 4s subshell. Same with the 4f, which came in after the 6s. The 4d, which came in after the 5s. Well, all of this happened because it follows an energy diagram, which means that for the 4s subshell takes less energy to fill the 4s subshell than it does to fill the 3D subshell. And lower energy is more preferable for anything. Now, the next rule that we need to follow is the Pauli exclusion principle. And this just states that no two electrons can have the same 4 quantum numbers in an atom, which in terms of orbital diagrams just means that 2 electrons cannot have the same spin direction. So in this case, helium is 1s2, which is, it can't be both up. Both electrons cannot be facing up. That's not possible. They have to be facing, one should be facing up and one should be facing down. And by convention, we always choose the first one to be up. So the second one's going to be down. Now, the third rule that we have to look is going to be Hund's rule. Hund's rule just states that every orbital in a subshell is singly filled before any of the orbitals is doubly filled, which is kind of how we sit on a bus, as in, whenever we sit on a bus, we always try to fill up all the empty seats before sitting right next to someone. So in other words, electrons begin to double up in an orbital because there aren't any more empty orbitals left in the subshell. So here's what follows. This diagram of nitrogen is what follows that rule. Right here, as you can see, there are 2 electrons which fill the orbital right here when there's an empty orbital right here. So this is not a possible one. That's wrong. Well, the second one is right. All right. Whenever we write an electron configuration, we always start with the shell number of the element, and afterwards we follow it by each subshell and the number of electrons within each subshell as a superscript. So for carbon, this is what it's going to look like. We're going to have, since there's 2 energy rings in carbon, there's going to be the 1s subshell which has to get filled. That's going to be 1s, and there's going to be 2 electrons which fill up the s subshell. And then we're going to have the second period, or the second shell, which has 2 subshells, which is going to be the S and the P. In the S, there can only be 2 electrons in total, and specifically for carbon, the P orbital, the P only gets filled in with 2 electrons. However, this can get, writing electron configurations for a lot of elements can get very long and messy if you follow this cycle. So there is this configuration called the noble gas configuration we can follow instead. And all this means is that we just write down the electron configuration after the predecessing noble gas. For example, in carbon, the noble gas configuration is going to look like, first we would have helium, which is the predecessing noble gas, and then 2s2, 2p2. I know carbon does not look very different in either of those forms, but if we have something a little bit more messy, like rubidium, these problems, the noble gas configuration can get very helpful. So in standard rubidium, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2. Note this 4s2 and 3d10 can be switched around because according to the alpha principle, we write down 4s2 gets filled in before the 3d10. But just by convention, I mean, whenever you write it down, something we always want to follow down 1s and then the 2s and then the 3s and then the 4s and then the 5s. So that's why I wrote it like this. So either of these methods work. And as you can see, rubidium is just krypton with 5s2. All of this right here is just krypton. We can also write specific configurations for ions. For example, when we have a neutral oxygen atom, we have 1s2, 2s2, 2p4. However, when we have an oxygen anion, we have a 1s2, 2s2, 2p6, which is the same as the electron configuration for neon. And that makes sense because neon and oxygen has the same exact amount of electrons. However, for cations, we're going to have first, for example, in neutral atom for iron, it's just going to be argon. I didn't want to write down the earlier stuff, so I just did the noble gas configuration. 4s2, 3d6. So I could have wrote down 3d6 and then 4s2. Either of those would have worked, but it's still. Okay, but for cations, what you're going to notice is we always remove electrons from the outermost shell. It's the 4s shell which gets removed first, and then the 3d, and then the 3p, and so forth. It's always going to be the outermost which gets removed first. It's not based off energy. I mean, it is based off energy, but the outermost is most easily removable. Now there are two major exceptions to these rules: chromium and copper. There are other exceptions as well. I mean, the elements underneath copper and chromium also follow these exceptions, but these are the most notable exceptions. So we would expect copper's or chromium's electron configuration to be something like argon 4s2 3d4. However, this is not what happens in real life. And we would expect coppers to be argon 4s2 3d9. This is not what happens, which you're going to notice in a setting. What you're going to see instead is going to be an argon 4s1 3d5 and argon 4s1 3d10 for chromium and copper respectively. And that's because the subshells are much more stable when they're either completely filled or half filled, and then when they are just partly filled. So right here, if we had a 3d4, that's neither half filled nor fully filled for the D subshell, which is just very hard to follow around. Whereas if you have a 4s1, that is still a half filled S subshell, so it's still quite stable. And 3d5, that's a very stable subshell as well. And right here we have 3d9, that's extremely unstable, whereas 3d10 is extremely stable, and 4s1 is okay stable. It's not as stable as 4s2, but it's still stable. All right, now let's just do some practice by writing down a few electron configurations and their orbital diagrams. So first, let's do lithium. So lithium has an atomic number of 3, which means that there's going to be, this is going to be a neutral atom of lithium. There's going to be exactly 3 electrons. And therefore, it's going to look like 1s2, 2s1. So right here, if you add up all of these electrons, that's going to be the number of electrons that you're looking for, which is 3. So it's 1s2, 2s1. Now we have a chloride ion, which is an anion of chlorine, which, if we write it down with a noble gas configuration, would look something like Ne 3. You always want to write down the S first. 3s2, 3p6. Remember, normally, just if it was just standard chlorine, it would have ended up with 3p5. But in this case, we have a chloride ion, so it's going to be 3p6. Now for Fe3+, remember, we always want to remove electrons from the furthest subshell, so the largest subshell, which in our case would be the 4s subshell. So instead of writing down we would be losing down electrons from the 4s2. So it would be argon 3d. 4s2 minus 3 is not, there is no such thing as a 4s negative 1. So you would just lose 2 electrons from the 4s, and then you would lose 1 electron from the 3d, which leaves you with 3d5. All right. Thank you guys for watching. I hope you guys learned something from this video.